Have you ever wondered how self-driving cars navigate busy streets? Or how virtual assistants like Siri and Alexa understand your commands? The answer lies in a powerful field of artificial intelligence called deep learning. Like a brain outside the skull, deep learning is transforming our world in extraordinary ways. Imagine a computer that can learn from experience, just like we do. Picture machines that can recognize objects, understand language, and even make decisions. This is the incredible potential of deep learning. Deep learning is already powering many technologies we use every day. It's helping doctors diagnose diseases with greater accuracy. It's enabling us to translate languages instantly. And it's even creating art and composing music that rivals human creativity. In this journey of discovery, we will unravel the mysteries of deep learning. Get ready to explore a world where machines learn, evolve, and reshape our future. Let's begin. At its core, deep learning is a powerful type of artificial intelligence that learns from vast amounts of data. This technology has revolutionized various fields, from healthcare to finance, by providing unprecedented insights and capabilities. Just as our brains learn from experiences, deep learning algorithms learn from data to make predictions and decisions. These algorithms are designed to mimic the way our brains process information, allowing them to handle complex tasks with remarkable efficiency. Think of it like this. Imagine teaching a child to recognize a cat. You start with simple examples and gradually introduce more complex ones. You might show them pictures of cats describing their features like pointy ears, a furry tail, and whiskers. Over time, the child begins to understand what makes a cat a cat. With enough examples, the child's brain begins to recognize the patterns that define a cat. This process of learning through examples is fundamental to how deep learning works. Deep learning works in a similar way. It uses layers of artificial neurons to process data, each layer extracting more complex features from the input. By analyzing massive data sets, these algorithms learn to identify patterns and relationships. This ability to discern intricate patterns allows them to make highly accurate predictions. The more data they are exposed to, the more accurate and sophisticated their predictions become. This continuous learning process is what sets deep learning apart from traditional methods. Unlike traditional computer programs that follow pre-programmed rules, deep learning algorithms can learn and adapt on their own. They are not limited by the constraints of their initial programming. This ability to learn from data is what makes deep learning so powerful and transformative. It enables machines to perform tasks that were once thought to require human intelligence. In essence, deep learning unlocks the hidden insights and knowledge buried within data, enabling machines to perform tasks that were once considered the exclusive domain of humans. From recognizing speech and images to making complex decisions, the potential applications are vast and continually expanding. Deep learning's magic lies in its ability to mimic the human brain, using artificial neural networks. These networks are designed to recognize patterns and make decisions in a way that is remarkably similar to how our brains work. By processing vast amounts of data, they can learn to identify complex patterns and make predictions with impressive accuracy. Imagine a network of interconnected neurons, each responsible for processing information. In the human brain, neurons communicate with each other through synapses, transmitting electrical signals that carry information. Similarly, in an artificial neural network, artificial neurons, or nodes, are connected by edges that transmit data. These artificial neurons, organized in layers, form the building blocks of deep learning. Each layer has a specific role, with the input layer receiving raw data, hidden layers processing this data, and the output layer producing the final result. The more layers a network has, the deeper it is, and the more complex patterns it can learn to recognize. Picture a neural network as a team of expert detectives trying to solve a case. Each detective specializes in a different aspect of the investigation, analyzing clues and sharing their findings with the team. Together, they piece together the evidence to solve the mystery. Each detective receives clues and passes their deductions to the next, gradually piecing together the bigger picture. In a neural network, each layer processes the data it receives and passes the results to the next layer, refining the information step by step. Similarly, data flows through the layers of a neural network, with each layer extracting and processing specific features. For example, in an image recognition task, early layers might detect edges and simple shapes. while deeper layers recognize more complex structures like objects and faces. The connections between neurons have weights, representing the strength of the relationship between them. These weights determine how much influence one neuron has on another, and they are crucial for the network's ability to learn and make accurate predictions. During learning, these weights are adjusted based on the data, just like strengthening connections in our brains when we learn something new. This process, known as training, involves feeding the network with data and adjusting the weights to minimize errors in its predictions. The network learns by adjusting these weights to minimize errors in its predictions. This is done through a process called backpropagation, where the network calculates the error of its predictions and adjusts the weights to reduce this error in future predictions. This iterative process of fine-tuning allows the network to become increasingly accurate over time. With each iteration, the network's predictions improve, and it becomes better at recognizing patterns and making decisions. Just as our brain's structure allows us to learn and think, the intricate architecture of deep neural networks enables machines to process information and make intelligent decisions. These networks are at the heart of many modern AI applications, from image and speech recognition to autonomous driving and beyond. By understanding how they work, we can better appreciate the incredible potential of artificial intelligence. Section 4. Layers of learning: how deep neural networks process information. Deep neural networks are composed of multiple layers, each playing a crucial role in processing information. These layers work in a hierarchical manner, where each layer builds upon the previous one to extract more complex features from the data. Think of these layers as specialized teams working together to solve a complex problem. Each team has a unique role and expertise, contributing to the overall solution by handling different aspects of the task. The first layer, the input layer, receives the raw data, such as pixels in an image or words in a sentence. This layer acts like our senses, capturing the initial information and passing it on to the next layer for further processing. This layer acts like our senses, capturing the initial information. Just as our eyes capture light and our ears capture sound, the input layer captures the raw data from the environment. Subsequent layers, called hidden layers, perform increasingly complex calculations on the data. These hidden layers are where the real magic happens, as they transform the raw data into meaningful patterns and features. Each hidden layer extracts higher-level features and patterns, much like our brains process information from simple details to complex concepts. For example, in the human brain, neurons work together to recognize shapes, colors, and movements, gradually building up to a complete understanding of what we see. For instance, in image recognition, early layers might detect edges and textures, while deeper layers identify shapes and objects. This layered approach allows the network to break down the image into manageable pieces and then reassemble them into a coherent understanding. This hierarchical processing allows the network to understand the data's intricate structure. By breaking down the data into layers, the network can focus on different levels of detail, from the most basic to the most complex. Finally, the output layer provides the final prediction or decision, such as identifying the object in an image or translating a sentence. This layer represents the culmination of all the processing and learning that has taken place in the previous layers. This layer represents the culmination of the network's learning and processing. It takes all the features and patterns extracted by the hidden layers and uses them to make a final decision or prediction. The depth of the network, meaning the number of hidden layers, contributes to its ability to learn complex patterns. The more layers a network has, the more complex the patterns it can learn, and the more accurate its predictions can be. Deeper networks can capture more intricate relationships in the data, leading to more accurate predictions. However, this also means that they require more computational power and data to train effectively. The balance between depth and computational resources is a key consideration in designing neural networks. Section 5. From pixels to predictions: real-world examples of deep learning. Deep learning is not just a futuristic concept, it's already transforming various industries and aspects of our lives. Let's explore some real-world examples that showcase its remarkable capabilities. Self-driving cars. Deep learning algorithms power the vision systems of autonomous vehicles, enabling them to perceive their surroundings, identify objects, and make driving decisions. These algorithms analyze data from cameras, sensors, and maps to navigate roads safely. Voice assistants. Virtual assistants like Siri, Alexa, and Google Assistant rely on deep learning to understand our voice commands, process natural language, and provide relevant responses. They learn from vast data sets of speech patterns and language models to improve their accuracy over time. Medical diagnosis. Deep learning is revolutionizing healthcare by assisting doctors in diagnosing diseases like cancer earlier and more accurately. By analyzing medical images like X-rays and MRIs, these algorithms can detect subtle abnormalities that might be missed by the human eye.